Storage is one of the biggest reasons computers feel fast, or painfully slow. But terms like SATA, M.2, PCIe, NVMe, and AHCI often make SSDs feel confusing instead of simple. In this video, we'll break down every SSD type, explain what each term actually means, why it exists, and how it affects real-world performance. No marketing claims, no unnecessary specs. SATA. SATA SSDs were the first storage upgrade that truly changed how everyday computers felt. Before they existed, most systems relied on mechanical hard drives. These drives were slow not because of bad design, but because of physics. Spinning disks, moving arms, and seek times meant every task involved waiting. Booting an operating system could take minutes. Opening programs felt sluggish. Multitasking was painful. SATA SSDs removed those mechanical limits. They connected using the same SATA ports that hard drives used, which made adoption easy. If a computer supported a hard drive, it could almost always support a SATA SSD without modification. This compatibility is why SATA SSDs spread so quickly when flash storage became affordable. In real-world use, the impact was immediate. Boot times dropped from minutes to seconds. Applications opened instantly. Older systems felt responsive again. For many users, switching from a hard drive to a SATA SSD was the single most noticeable upgrade they ever made. However, SATA SSDs inherited one major limitation from the interface they used. SATA was never designed for flash storage. Its maximum throughput caps out around 550 megabytes per second, regardless of how fast the memory chips inside the drive are. Once that ceiling is reached, performance can't scale any further. Today, SATA SSDs are no longer cutting edge. They are best suited for older systems, budget builds, or secondary storage. They remain reliable, affordable, and widely compatible. But they represent the starting point of modern SSD evolution, not the end. AHCI. To understand why early SSDs hit performance limits so quickly, you have to look beyond the drive itself and examine how it communicates with the system. That communication layer is known as a protocol. And for early SSDs, that protocol was AHCI. AHCI stands for Advanced Host Controller Interface. It was created long before SSDs became common and was designed specifically for mechanical hard drives. At the time, this made perfect sense. Hard drives were slow, sequential devices, and AHCI was optimized to handle that kind of workload reliably. The problem is that flash storage behaves very differently. AHCI can manage only one command queue, with up to 32 commands at a time. For a spinning disk, that was more than enough. But SSDs are capable of handling thousands of requests simultaneously. When paired with AHCI, that potential is effectively throttled. This mismatch created a bottleneck. Even as SSDs became faster internally, AHCI prevented them from fully using that speed. Latency stayed higher than necessary. In simple terms, the drive was ready to work faster, but the protocol couldn't keep up. Despite these limitations, AHCI remained dominant for years because it offered something critical: compatibility. It worked on nearly every system, required no major changes, and was extremely stable. Every SATA SSD you've encountered operates through AHCI. AHCI wasn't flawed, it was just outdated. As SSD performance continued to improve, it became clear that a new protocol was needed. That realization set the stage for the next major leap in SSD technology, M.2. One of the biggest sources of confusion in modern storage comes from a simple misunderstanding. M.2 does not mean fast. M.2 is not a performance standard, a protocol, or a guarantee of speed. It is a physical form factor, the shape and connector of the drive. An M.2 SSD is that small, stick-like piece of storage that mounts directly onto the motherboard. There are no cables involved, which makes it ideal for laptops, compact systems, and clean desktop builds. From a design perspective, M.2 was a major improvement over bulky 2.5-inch drives and SATA cables. But performance depends on what runs through the M.2 connector, not the connector itself. An M.2 slot can carry different technologies. Some M.2 SSDs use the same SATA interface as traditional 2.5-inch SSDs. These drives are still limited to roughly 550 megabytes per second, just like their larger SATA counterparts. The only difference is physical size and cabling. Other M.2 SSDs use PCIe and NVMe, which allows much higher speeds. This is where most people get confused. When buying an M.2 drive, the form factor tells you how it connects physically, not how fast it will be. Two M.2 drives can look identical and perform very differently depending on whether they use SATA or PCIe with NVMe. M.2 simplified system design and enabled faster storage solutions, but on its own it says nothing about performance. To understand speed, you have to look at what comes next. PCIe. Once SSDs outgrew the limits of SATA, they needed a faster path to communicate with the CPU. That path is PCIe, short for Peripheral Component Interconnect Express. PCIe is not exclusive to storage. It's the same interface used by graphics cards, network cards, and other high-performance components. What makes PCIe different from SATA is bandwidth. Instead of a single shared channel, PCIe provides multiple lanes that data can travel through simultaneously. Each new PCIe generation increases how much data each lane can carry. With 4 lanes, PCIe 3.0 can deliver around 3,500 MB per second. PCIe 4.0 roughly doubles that to 7,000 to 7,500 MB per second. PCIe 5.0 doubles it again, approaching 14,000 MB per second. Compared to SATA's fixed 550 MB per s ceiling, the difference is massive. Large file transfers, game loading, video editing, and data-heavy workloads all benefit when storage is no longer constrained by a narrow interface. However, PCIe introduces new considerations. CPUs and motherboards only have a limited number of lanes. When multiple devices compete for them, bandwidth can be shared or reduced. Power consumption and heat also increase as speeds climb, especially with newer PCIe generations. Despite these trade-offs, PCIe became the foundation of modern storage because it scales. As flash memory improved, PCIe ensured the interface wouldn't be the limiting factor. It provided the highway. But a highway alone isn't enough. To truly unlock SSD performance, a new language was required: NVMe. NVMe is the final piece that explains why modern SSDs feel dramatically faster than anything that came before. NVMe stands for Non-Volatile Memory Express, and unlike AHCI, it was designed specifically for flash storage. It does not reuse hard drive era assumptions. Instead, it treats SSDs as what they actually are: extremely fast, highly parallel devices. The most important difference is how NVMe handles commands. While AHCI supports a single command queue, with up to 32 requests, NVMe supports up to 64,000 queues, each capable of holding 64,000 commands. This allows modern CPUs to issue and process massive numbers of storage requests simultaneously without waiting in line. Latency is also dramatically reduced. This is why NVMe drives don't just look faster in benchmarks, they feel faster in everyday use. Systems boot quicker, applications launch instantly, and heavy multitasking no longer causes storage-related slowdowns. NVMe typically operates over PCIe, which gives it the bandwidth needed to scale. Together, PCIe and NVMe allow SSDs to perform at speeds that were impossible just a few years ago. However, NVMe doesn't automatically make every system feel faster in every situation. For light workloads, the difference between SATA and NVMe can be subtle. The biggest gains appear in tasks that involve large files, frequent reads and writes, or parallel workloads. NVMe represents the moment storage stopped imitating hard drives and started behaving like the high-speed memory technology it truly is. When you strip away the acronyms, SSD technology follows a clear and logical progression. SATA SSDs replaced mechanical hard drives and delivered the first real leap in everyday responsiveness. AHCI was the inherited language that made those early SSDs compatible, but also limited their potential. M.2 changed the physical design, making storage smaller and cleaner, but didn't guarantee speed on its own. PCIe removed the bandwidth ceiling, giving SSDs a fast, scalable path to the CPU. And NVMe finally gave flash storage a protocol built specifically for its strengths. Each piece exists for a reason. Confusion only happens when they're mixed together without context. So what actually makes sense today? If you're upgrading an older system, a SATA SSD is still a massive improvement over a hard drive and often the most cost-effective choice. If you're building or buying anything modern, an NVMe PCIe SSD is the clear standard. It offers faster load times, better multitasking performance, and long-term relevance as software continues to demand more from storage. What matters most is not chasing the highest numbers on a spec sheet, but matching the storage type to your system and workload. An expensive PCIe 5.0 drive won't feel faster if the rest of the system can't take advantage of it. At the same time, cutting corners on storage can bottleneck an otherwise powerful build. Once you understand how SSDs evolved and what each term actually means, choosing the right drive stops being guesswork. It becomes a practical decision, one based on how your system is actually used, not on confusing labels or marketing claims. Once storage stops being the bottleneck, every other limitation becomes easier to see. And that clarity is exactly what modern storage was designed to deliver. You now understand how storage evolved, and why modern systems feel fast the moment you remove mechanical and protocol bottlenecks. Boot times shrink, games load instantly, files open without delay. But once storage stops holding your system back, another limitation becomes obvious: your display. What's the point of loading into a game instantly if motion still feels blurred? Why render frames faster if your panel can't show them clearly? And how do terms like IPS, VA, TN, OLED, Mini LED, and QD OLED actually affect what you see? In the next video, we're breaking down every display panel type the same way we did RAM and SSDs. What each technology is, why it exists, and which one actually makes sense depending on how you use your system. No marketing claims, no spec overload, just clarity.